Day 65 notes, probability and statistics. Today I have guided notes that I'd like for you to fill out along with me while completing this video today. And this has to do with what we call confidence intervals. As we discovered yesterday with the pennies project, we found that when only a single sample is selected or is collected, the estimate for population parameter might not be very good. For example, if we took just one of those samples yesterday, the average age of that penny might not actually represent the average age of all pennies in a population. And so what we do is we use a confidence interval, because a confidence interval is a range of values used to estimate the true value of a population parameter. So we use this range to estimate where the true average age would have been. Now, the most common confidence level that we use in this class is 0.95 or 95% confidence. And that is to say that we are 95% certain that a particular population's parameter will fall in the calculated range based on several examples used to compute the estimate, rather than just one. For example, with a 95% confidence interval, we assume that out of 20 samples to find a true population parameter, only one confidence interval, or one of those samples, would not contain the actual population parameter. And we can illustrate that with this diagram here. This is similar to the chart that we created yesterday in the penny project. But what we have here are confidence intervals. There are 20 of them. So if I count each of these samples, these are different confidence intervals that are calculated. Now, we don't know this, but let's suppose that a particular population parameter, let's say that this is a proportion of the number of heads that would occur when flipping a particular coin. That proportion is 0.5, so half the time we'll flip heads and half the time we flip tails. This person here in this first example has a confidence interval that contains maybe a low range of this result, 0.43, and a high range of maybe 0.54. So they're saying that the true population's parameter is going to fall between this point and that point, and they would be correct because the actual population parameter does fall in between those two. This next person then had a slightly different result, but they were 95% confident that the true population parameter fell between those two, and it would have worked there as well. Same thing with all of these green bars. In every green bar here, the actual population parameter falls somewhere in between the two endpoints on those green bars. And the only exception to that is this one red calculation here. Somehow or another, the samples that were collected by this person that did the example in red, or the actual population parameter did not fall in between these two endpoints that were calculated by that person. So this is the one time out of 20 in which the actual population parameter did not fall between the two endpoints as expected. So this is that one person out of 20. The other 95% of the people doing this study actually obtained that population parameter. Now, each confidence interval is constructed using alpha, and alpha is the complement. It's the complement of the confidence level. And so our confidence level in that last example was 95%. So other confidence levels that we often use are 90% and, oops, this should read 99% here. Let me fix that on my screen. I think yours is correct. So that should say 99% and 95% here. So anyway, if the confidence level is 90%, if we're 90% confident, or if we have a probability of 0.90, then alpha in this case has to equal 10% or 0.1. If the confidence level is 95% or 0.95, then alpha is equal to 5% or 0.05. And finally, if the confidence level is 99%, then alpha is equal to 1% or 0.01. Now, this alpha calculation is important to the formula that we use here in just a few minutes. We're very interested in this complement, so identifying alpha given a particular confidence level is important. Now we'll use this alpha to identify what's called a critical value. The critical value associated with a confidence interval is denoted with this z and a subscript of alpha divided by 2. So this is where alpha comes into play. And again, it's used to identify the location of each tail within an appropriate normal curve. So in this example here, if I have a confidence level of 95%, then that means that alpha was equal to 5%. So if we're sure that a population's parameter falls within these two marks, if we're 95% sure that it falls between those two marks, then there's a 5% chance that it doesn't fall within those two marks, that it lands over here to the right or to the left. Now, the reason why we cut it in half, we cut the 5%, that alpha, in half, is because, well, half of that 5% falls to the right of this tail, and half of that 5% falls to the left. So we have an area to the left of this mark, which is equal to 0.025, and an area that falls to the right of this mark is also 0.025, or 2.5%. Now we can use a z-table or the calculator to find this result. This is the critical value that was mentioned just a moment ago. If we used our calculator, we would use the menu 653 command, because we can provide the area, a mu, and a sigma in order to identify this particular z-score. And we need this z-score for the calculation of our confidence interval, which we see here in bullet point number 9. For a population's mean, which we'll mark with mu, the margin of error is calculated. E for error is equal to this z alpha divided by 2. This is that critical value that we found just a moment ago, times, sorry about that, times sigma divided by the square root of n. So this is the formula that we're going to use for our population mean, discovering our population mean. And then the confidence interval then is calculated with the x-bar, the sample mean, or the sample average, plus or minus this confidence, or I'm sorry, this margin of error. Or in other words, x-bar plus or minus z sub alpha divided by 2 times sigma divided by the square root of n. Now this may seem like an intimidating set of equations, but really it's not too bad. Most of you, I believe, did write these formulas down from yesterday's video. So if you didn't do that already and add it to your vocabulary sheet, please do that now, your formula sheet. Do that, please, so that you have this ready to go for the SLO that we complete next week. Now I'm going to stop the video here and then resume in a second video where I walk through a couple examples utilizing these formulas.